so the topic now is forces on threaded ring. In this topic, we would have, like the topic suggests, there would be thread, there would be ring. For example, you might have a setup like this where there's a thread passing through a ring like this. So then we'll, of course, have tension in the string. Tension points away from the object, so there should be tension in this direction, T, tension in this direction, T. If it's mentioned that the ring is smooth, if ring is smooth, then tension is going, then tension is equal. So in this case, that means that the ring is smooth. So both the tension on either side of the ring is going to be equal. If it isn't mentioned that the string is smooth, then the tension would be unequal. You will have to call one tension T1 and the other one T2. So for a smooth ring, the tension on either side of the string is same. Okay. So that means in a setup like this, if this is smooth, then this would be T and this would be T. However, if the ring is rough, let's say this is rough, then you'll have to call this T1 and this T2. In case an isosceles triangle is forming, if this is an isosceles triangle, in isosceles triangle, tension is also same on both sides of string, on both side of ring. Even if ring is rough. So if the triangle given in the setup is an isosceles triangle, then even if the string is rough, the tension on either side of the string is going to be T. Okay. Then there is a theorem which is called Lemmy's theorem. So now, again, let's consider the same setup. There's a ring, there's tension. Let's say the string is rough. Then this would be T1, this would be T2, and this is the weight acting on the object. Sorry, the downward weight of the ring. So when there are only three forces acting at a point, then only three forces are acting on a point, then Lemmy theorem says that T1 upon sine, let's call this angle theta 1, will be equals to T2 upon sine. I'm calling this angle theta 2 is equals to the third force, which is weight, upon sine. I'm calling this theta 3. So Lemmy's theorem is applicable in a setup where only three forces are acting at a point. If the forces are two, or if the forces are more than three, four or five or six, then you cannot apply this theorem. It only works when there are three forces acting at a point. Okay. Lastly, you would need to resolve the tension into its components. So let's say this is T1, this is T2, and you're given this angle, let's say 30, and let's say 40, for example. Then you will have to resolve the tension into its component, both the tensions. So this one gets resolved into this and this. So one of the component is this. This is the opposite component. So that means it's the sine component. So this is going to be T sine 30. Then there's this component, which I'll instead draw over here. So this is the adjacent component or the base component. So it's going to be the tan component. T cos 30. Similarly, this gets resolved into this and this. But the vertical one, I want to instead draw over here. This component and this component. Okay. Now this is the opposite to the angle. So it's going to be T2. Okay, the first one should have been T1 and T1. So this one is going to be T2 sine 40. And this one is the base or the adjacent component, which is the cos component. So T2 cos 40. There's also going to be a weight in the downward direction. So mg downwards. There isn't going to be any normal contact force now because there's no contact with the surface. The ring is levitating in the air. So there's going to be no normal contact force. No R, which is the normal contact force, because ring is not in contact with any surface. Okay. Then you might get a case like this, that there's a rod and there's a ring. And there's a pull in this direction. Let's say this is T and this is, let's say, 30. So then the components would be this component, which is T, that's the opposite component, so T sine 30. And this one is going to be the base component or the adjacent component, T cos 30. Okay. If you're told that, okay, there's also weight acting downwards, mg, or the weight. And now there's a contact between the string and the rod. There's a contact over here. So there's going to be an R in the opposite direction. So there's going to be an R here. Let's say you're told that this ring, and even if you're not told, you know that when the ring moves, it moves left because of the direction of the tension mentioned. If you're told that the rod is horizontal, the rod is rough, then that means there's also friction in the rod, which acts in the opposite direction, which is going to be mu r. So the friction is opposite to the direction of motion. So left side pe is going to be mu r. So you're going to use forward force minus backward force equals to ma, depending on what is being asked. Then you might get a setup like this instead. That here's the rod, it's now vertical. Here's the ring now, which is being pulled in, let's say, this direction. So then this is T, and let's say this angle is given, which is 30 degrees. So then the components would be, this is the base component or the adjacent component, so the cos component. No, actually, no, it's the opposite component because it's over here. And this is the base component. So this is going to be T sine 30 because it's opposite. And then upwards, there's going to be T cos 30. Okay. Then the weight is going to be in this direction, mg. The normal contact force is perpendicular to the contact. So now the ring is in contact over here. This is the contact. So this has to be R. So R is going to be in this direction. And according to the tension, the direction of the tension, we can tell that the rod would move upwards when it moves. So that means friction is going to be opposite. So there's also a mu r in this direction. So now again, accordingly, you'll be using forward force minus backward force is equals to ma. I'm going to copy the first question of the worksheet. A ring of mass 1.1 kg is threaded on a fixed, rough horizontal rod. Rough means there is friction. 1.1 kg indicates that there's going to be a weight in this direction, which is mg. So weight will be 11 newtons. So 11 newtons is a force in the downward direction. So we can tell from the direction of the pull, this pull, that it's going to be moving in this direction. So that means since the rod is rough, there's friction in this direction. Call it F is equals to mu R. Okay. Then the tension is already mentioned. It's 13 Newton at an angle alpha with the horizontal, where tan alpha is 5/12. Now, when tan alpha is given, you can use it to find sine alpha and cos alpha. And that will help you in finding the components of tension, because we know there's this component of tension and then there's this component of tension. The opposite one is the sine component, and the other one, the adjacent one, is the cos component. So I'm going to draw cos component in the same direction, but the sine component in this direction instead of drawing it here. Okay, so that is going to be 13 cos alpha, 13 sine alpha. Okay, now tan alpha will help us find the value of cos alpha and sine alpha. How? Tan alpha is 5/12, so draw a random right angle triangle. That's if this is alpha, then it's 2, so opposite over adjacent. 2. Okay, now we can use Pythagoras and find this third length, which is going to be 5 square plus 12 square, which gives 13. This is going to be 13. So that means sine alpha would be, so opposite over hypotenuse, or some people have perpendicular over hypotenuse. And cos alpha is adjacent over hypotenuse or base over hypotenuse. So now, instead of 13 cos alpha, I'm going to write 13 times cos alpha is 12/13. And sine alpha, instead of that, I'm going to write 5/13. Okay. Also, I have had to draw R. R is going to be pointing. Let's see where the contact is. The pull is in this direction. So the contact is in this direction. So R is in this direction. R is going to be pointing upwards, normal to the contact. So the ring will be in contact with this rod over here. So R has to be over here. So there's an R vertically upwards. There is an R here. This would be R. Okay. Now let's see what the question is asking. The ring is in equilibrium. That means all the forces are balancing each other. Left forces are balancing the forces on the right. up forces are balancing the down forces. So it's just forward force equals to backward force. Find the frictional component of the contact force on the ring. That just means find friction. Find FR. Oops. Okay, I did not realize. Was I muted all this time? I don't.
No, no.
अच्छा ठीक है
No.
आवाज नहीं थी ओके ठीक है अच्छा so part 1 says find frictional component of the contact force of the ring. This just means find friction. Okay, so friction is acting in this direction, right? And the left force balancing is just 13 cos alpha. So friction equals 13 cos alpha, and we already know what cos alpha is. It's 12 over 13. So friction is just 12 newtons. Part 2 is find the normal component of the contact force. So that's the normal contact force, which is acting upwards, and the forces balancing are 11 Newton weight and that 13 sine alpha component of the tension. So R is equals to mg, the weight, plus 13 sine alpha. And we know that sine alpha is 5 by 13. So R is going to be 11 plus 5, which is 16 newtons. Part 3. Given that the equilibrium of the ring is limiting, limiting equilibrium just means that now you have to use the friction actual formula mu R, because this formula is only applicable on limiting equilibrium. Okay, given that the equilibrium of the ring is limiting, find the coefficient of friction between the ring and the rod. So now you have to find the mu. So friction is equals to mu R. Friction we had already found in the first part 12 equals mu R we had found in the previous part. So mu will be 12 by 16, 6 by 8, which is 3 by 4. So mu is 3 by 4 or 0.75. That is question number 1. Please let me know if you have any questions.
No questions, ma'am.
Okay. Then let's take a look at question number 2. A light, inextensible string has its ends attached to two fixed points, A and B, with A vertically above B. A smooth ring. Now, if the ring is smooth, that means the tension on in the wires is going to be the same. So this is the wire or the string. So the tension on either side of the ring is going to be the same. Tension points away from the object. So this is T and this is T. The tension is the same. So we're not going to write T1 and T2. If the ring was rough, we would have to write T1 as tension in one of the string and T2 as the tension on the other part of the string. Okay. So the ring is smooth and has a mass of 0.8 kgs. So this is going to be pointing downwards as mg. So there's an 8 Newton of force acting downwards, which is the weight. Is threaded on the string and is pulled by a horizontal force of magnitude x newtons, as we can see in the figure. Since x is horizontal, so we will not be resolving it into any components. It's just a right direction force, a force acting in the right direction. There's no theta with it, so there's no resolving that needs to be done. Sections AR, RB on the string make angle 50° and 20° respectively with the horizontal as shown. These angles will help us resolve both the tensions. So for this, there's a component in this direction and there's a component in this direction. Or instead, let's take a look, let's form this as our triangle. So then there's a component in this direction and there's a component in this direction. The up component is going to be the opposite component since it's opposite to the angle. So opposite component is always the sine component. So there is a vertically upward force acting, which is T sine 50. Then there's a force acting on the left, which is the adjacent force. So it's going to be T cos 50. And instead, I'm drawing it here. T cos 50. Then there's a right angle triangle being formed here. Here's the original tension, here's the downward component, and here's the left component. I'm going to draw the left component here instead. Okay. So the down component is the opposite component, so that is T sine 20. The left component is the adjacent component, which is going to be T cos 20. Okay. There is no rod now, so there's no contact with the rod or the ground. So there's no normal contact force now. All right, there's just a string passing through a ring. It's not connected to a rod. So there's no contact between the ring and anything else. So there's no normal contact force in the question. Okay. The ring rests in equilibrium. That means all opposite forces are balancing each other out. So up force equals down force, left forces equals right forces. Okay, find the tension in the string. So for the tension, we can equate the up and down forces. So T sine 50, which is the only up force, equals 8 plus T sine 20. This should be the equation. I'm going to move the t's on both on the same side, and I'm going to take t common. So t sine 50 minus t sine 20 on the left of the equation, and then take t common. T equals 8 upon sine 50 minus sine 20. 8 upon sine 50 minus sine 20 minus 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 sine 50 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 min which is equals to 18.9 newtons after rounding. The unrounded value is 18.8668. So that's 18.9. Part 2 says, find the value of x. So x is the right force, the only force at the right, equated to the left forces, which are 2 cos 50 plus t cos 50 plus t cos 20. We know what t is. T is 18.8668. So then substitute it in the equation and get x equals 29.8564, rounds to 29.9 in 3 significant figures.